Hey everyone, so this is going to be the lecture for 2.2. I am going to screen share the notes. Obviously on your end, you are always welcome to open up the notes so that you can have those or you can print them. It's whatever works for you, but 2.2 is very I don't know how to, I guess, note heavy in that there's a lot of just definitionary style notes. And to save myself having to rewrite them again on the board, I'm going to screen share them with you. And then I will do the problems on the board. That way you can see me work out the problems live, but you also have the nice graphs and pictures that I drew in the paper instead of the ones that I'm going to draw on the board, which won't be nearly as nice because there's no lines and things. So this is section 2.2, which is over more functions and graphs. And so we're going to talk about different kinds of functions and how they interact with each other and what that means when we are graphing them or looking at them algebraically. So if we look at the notes, it did copy a little crooked, so I do apologize for that. But the first thing we're going to talk about is increasing, decreasing, and constant functions. So these are kind of logic. And as long as you're looking at it from left to right, it's going to make sense. So think about when you read a book. You read a book from the left to the right. So the same thing is going to be true about your functions. You're going to look at a function like this increasing one, and you're going to go from the left to the right. So it says a function is increasing on this open interval. So any interval we choose from, if f of x, so notice f of x1, that's your y value. So the y value at that point, x1, is less than the y value of your x2, and your x1 is less than your x2 for any given 2 points you can pick on that interval. Basically, is this point lower on the graph than this point? If that's true, then it's an increasing function. If you look at it like reading a book, if you were walking along your function and you're starting on the left-hand side and you're walking, are you going to be walking uphill? If the answer is yes, then it's an increasing function. You're increasing from the left to the right. The same thing is true in reverse for a decreasing function. Again, you read from the left to the right, and you are decreasing if you're going down the hill, or if your y value at your x1 spot is greater than the y value at your x2 spot. Thus, it's decreasing. A constant function is a flat road. Nothing, your y's do not change. So in a graph, you can have all three of these things happening along different intervals, and that is completely fine. And we'll actually do problems like that where we have to identify the sections where it's increasing, decreasing, and neither. We're actually getting ready to do that in just a minute. But this is how you do it. So if you're going uphill from left to right, it's increasing. If you're going downhill from left to right, it is decreasing. And if you're walking along a flat road, then it is a constant function. And so what we're going to do is we are going to, I'm going to make that big. We are going to find those intervals where that is true on each of our graphs. Okay. So I have two examples to do that. There you go. These are the same examples that are in the notes. So if you want to just scroll down on your notes, if you have them open, that's fine, or you can copy off the board. But I will work through it. So for this style of problem, you're going to find the intervals for which it's increasing, decreasing, and constant. So what I always recommend doing is I recommend starting on the left side of your graph and just pretending like you're walking it and figuring out how you're walking your graph. So if I do that, if I start all the way over here on the left side, what am I doing first? Well, I'm walking downhill. Well, I'm walking downhill until where? Until I hit 0. Then I start walking uphill, and then I start walking downhill again. So I am decreasing. And what is the interval that I'm decreasing on? Well, negative infinity. So I can go out as far as I want, all the way down to 0. At 0, I switch and I start increasing. And I start increasing. How far do I keep increasing? Until I hit, and notice we're using our x values. For increasing, decreasing, and constant, we're going to use our x values here, okay? So I'm increasing until I hit that topmost part of this crest, which is going to be at the point 2. So I increase from 0 to 2. And then I'm going to decrease. I'm going to start walking downhill again. So then I'm decreasing again from 2 all the way to positive infinity. So in this graph, we have 2 different sections that are decreasing and 1 section that's increasing, and we don't have a constant section, and that's okay. Our graph can do multiple different things throughout its life as a way to think of it. But you do use your x values and you do use interval notation because we are finding the interval. Notice though, I always use parentheses on these 2 situations because they are switching right then. And so it can't be increasing at that point and decreasing at that point. So we just use parentheses to justify that. Okay. What about our second graph? Our second graph, we have a flat line right there at y equals 2. And then we have an open circle with an arrow up after that. Well, that means if I start at the left side, I'm just walking a flat road. That means we have constant, our function is constant from negative infinity all the way until 0, until we hit that y-axis. And then after we hit that y-axis, we jump down here and we start going up again. So then it is increasing from 0 all the way to infinity. This style of graph is called a piecewise graph, and we will do more with that at the end of the lesson today on how these work and how we graph them. So start with the left, follow your graph, see if it's increasing, if it's decreasing, if it's constant, and then write the interval in respects to your x values with that. I'm going to scroll. As you can see, there's my work. There's my work again. I wanted to talk about relative minimum and relative maximum. These are, again, it's easier to show you in my notes than it is for me to remake my notes on the board. And these are kind of, they go very much with the increasing, decreasing, and constant. And they're kind of logical in that a relative or local maximum, so local means in a given area, is the y, like a function value f of a is a relative or local maximum of f if there exists an open interval containing a such that the f of a is greater than the f of x for every x that's not equal to a in that open interval. AKA, is there an area around the highest point on your graph that you can look at that all of the y's are smaller than that one value? If so, then you have a relative maximum. Basically what you're looking at then on your graph is the tippy top. So on our first one, where it decreases and then it increases again, we kind of have that hill. So at the very top of that hill, right here where it's 2 and 4, if we just looked at this, that is a relative maximum. Is it the maximum for the entire graph? No, because this goes on for infinity, and so there is something higher than that at certain points. But if I'm just looking at this part of my graph, then that would be a relative maximum, the highest value that you could get. And that's what that means. I can do the exact same process for a relative minimum. That is the lowest point in a given section of our graph. Again, on this first one, we would have a relative minimum right here. That's where it switches from decreasing to increasing. And on this section of the graph, I would have a relative minimum. If I included this section of the graph, that would not be a relative minimum because there would be a lower value than that. So it's just within that one interval that we have that relative minimum. These are going to be obvious when you're looking at the graphs on whether it's a minimum or a maximum. And it's going to be like, it's going to be obvious for you. It's not going to be one of these tricky things of like, oh, I don't know if that's smaller than this. It's going to be noticeable. And I will show you one example of that. And plug that and break my charger. Not really. All right. Is that too far over? Probably. Sorry. It's hard to know which desk to put these on because I'm going to have it back far or it's going to be crooked. So I do recommend pulling up my notes so that you can see it in person. But for this W-shaped graph, we are going to find the relative max and the relative min. You can have more than one relative max and more than one relative min. That is totally fine. Let's start with the max. If we look at a W, where would we have a relative max? That doesn't mean the highest point on the graph because our graph extends upward for infinity. It just means in the relative scheme of things, like where is it shifting from increasing to decreasing and vice versa. So if we're following our graph, actually, I think I'll write both out here so we can just do them as we hit them. If I start on the left and I come down, we're decreasing, decreasing, decreasing until right here at -3. So that means that we are decreasing until that point. So that's going to end up being a relative min at the point -3, 0. So for increasing, decreasing, and constant, we're listing intervals. For relative maximum and minimum, we're listing points because that's the point where it is the relative min or the relative max. After this point, we start increasing again. And we increase all the way up until we hit the point 0,4. That 0,4 is the maximum point on that part of the graph. So that is our relative max. From there, we start decreasing again, all the way until we hit the point 3,0. That is another relative min. And then we start going up again and we increase forever. So in this case, we have one relative max and two relative mins. And hopefully you can kind of see how that works on the graph with those chunks. Okay, the next topic when it comes to graphs and functions is something called symmetry. When something is symmetric, it means it's the same on both sides. And so graphs can be symmetric. They can be symmetric about the y-axis, which is the vertical one. So think about folding your paper in half tall-wise. They can be symmetrical about the x-axis, which is horizontal. So think about folding your paper in half the fat way. Or they can be talked about as being symmetrical across the y = x line, which is like the perfect diagonal through the Cartesian coordinate system, which would be, if I had a square piece of paper, like folding it corner to corner if it's square. And so what does this mean? Well, if you are symmetric about the y, so the vertical axis, that means that for every x, y you have on your graph, there's also a negative x and a positive y that's also on the graph. And we test this by substituting in a negative x value in for our x value. And if we get the same equation out, then that tells us that we're symmetric about the y-axis. And as you can see, there's a very generic graph where it shows you the two swoops like this, where it is symmetric about the y-axis. And notice we have the point xy over here, which means we have the point -x, y here. So the y stay the same because we're about the y, and our x's change from positive to negative if you're symmetric about the y. So similarly, if you're symmetric about the x, that's your horizontal, so you're folding this way, up and down. So for every xy on the graph, there's an x negative y. So our y's are what's changing this time instead of our x values. So in this case, we substitute in a negative y for our y's in the equation. And if we get the same equation out, then we know it's symmetric to the x-axis. Symmetric to the origin, or symmetric to the y equals x line, means that for every x, y on our graph, there's a negative x and a negative y that's also on our graph. So in this case, you would do both. So if you substitute in the negative x and the negative y for your x and y and get the same equation, then you know it's symmetric about the origin. So notice, like, if we folded our paper this way, those two graphs would lay on top of each other. So we need to determine the symmetry for a given equation. Now, if you're looking at a graph, sometimes you can tell that it's symmetric. Like our W, this last one, if we folded our paper this way, our W would lay on top of itself. So that tells us that we are symmetric about the y-axis. But this one over here, this piecewise, isn't symmetric about anything. No matter how you fold it, it's never going to lay on top of each other. So if you're given a graph, sometimes you can just look at it and determine it. But if you're given an equation, that's where you're going to have to do some substitution and solve and see if we get the same thing or not. So if we want to check if it's symmetric about the y-axis, then what we're going to do is we are going to substitute in negative x for x, and this is for the y-axis symmetry. So here's our original. We have x equals y squared minus 1. And what we want to do is we want to put in a negative x anywhere there's a positive x and see if we get the same thing. So we have negative x equals y squared minus 1. Look at x by itself so that it looks like our original by multiplying everything by negative 1. When we do that, then we need to look at these equations. Is this top equation the same as this bottom equation? This top one is the original, x equals y squared minus 1. Is that the same thing as x equals negative y squared plus 1? No, it's not. Those are not the same. So it's not symmetric about the y-axis. Now we have to test the symmetry to the x-axis. And when we do that, what we're doing is we are substituting in a negative y for our y's. And that's if we are symmetric about the x-axis. So they're kind of flip-flopped. You're checking symmetry for your y, so you're going to switch your x's. You check symmetry for your x-axis, so you switch your y's. So again, the original equation. Now anywhere there's a y, I'm going to plug in a negative y. And then I look. Is the top equation the same as my bottom equation? In this case, it is the same. So that means they are symmetric about the x-axis. Now this next one, hopefully you could already tell me if it's symmetric to the origin or not. Because to be symmetric to the origin, you have to be symmetric to the x-axis and the y-axis at the exact same time. However, we're still going to do it so that you can see why it works. So you're going to do negative y for the y and negative x for the x, and that tells you if you're symmetric to the origin or not. So we have x equals y squared minus 1. So I'm going to have a negative x in there and a negative y in there. Negative x equals y squared minus 1. X equals negative y squared plus 1. That does not equal the top one. They are not the same. So not symmetric to origin. typically, if you're checking symmetry for your y-axis and you get that it's not symmetric, then you know it's not going to be symmetric to your origin. Or if you get that it's not symmetric to your x, it's not going to be symmetric to your origin, because it has to be symmetric to both of these to be symmetric to your origin. But it's always good to check to make sure you didn't accidentally mess up somewhere, because if you got that it was symmetric to the origin, but you got that it wasn't symmetric here, then either you messed up here or you messed up there. And so it is a good way to kind of check back on yourself to make sure that you did it right. Okay, so that's symmetry. So we've done increasing, decreasing, and constant. We've done relative min and relative max. Now we've talked a little bit about symmetry and how that works. And now we're going to talk about even and odd functions. So an symmetric to the y-axis, so that's where, oh, there goes chalk. Symmetric to the y-axis is where you fold your paper the tall way. That means you have an even function. When we did that, that means our f of negative x was the same as our f of x. So remember on our, right up here, our symmetric to the y, when we folded, our y's didn't change. And that's all it says down here. Even means our y's don't change. If we are symmetric to the origin, that tells us that we are an odd function. That means our f of negative x equals negative f of x, okay? And then we have neither. If it's not even, if this doesn't work, or if it's not odd and this doesn't work, then we're something called neither. So here's 3 examples, the general examples. So here is an odd function. What we have is we have negative x and we have negative f of x. So we have negative y at that point. And this is our x and our f of x, okay? If we're even, then it's our y's that stay the same and our x's are negatives of each other. And if we are neither, then it can look something kind of like that, okay? We are going to do an example so we can see how we are even, odd, or neither. And then I'll give you a really helpful little cheat that makes it a lot easier. But first you have to learn the hard way, or the math way. All right. There you go. Let's see if I can make this any bigger. I can't. So again, pull it up if you can't see. I will write big. We need to identify if these equations are even, odd, or neither. And the way that you do that is you're going to plug in a negative x for the x in the equation and see if you get what you get out at the end, okay? So I'm going to do f of negative x. So anywhere there's an x, I'm writing negative x. And then I'm going to simplify. Negative x to the third is going to give me, whoops, I don't need that parenthesis anymore, negative x to the third. Because a negative number times a negative number becomes a positive, times a negative number becomes a negative again. Negative 6 times a negative x will give me a positive 6x. So at this case, now we need to check, does my f of negative x equal my f of x? My f of negative x is this bottom. Is this the same as my original? No, it's not. And since it's not equal, that's good. We don't want it to be equal because we want to check to see if it is even or odd. So it's not equal. But what we did show was f of negative x equals negative f of x. All we did was we took a negative times everything in our original equation. And when it looks like that, that tells us we're an odd function. So if you can multiply the original equation by a -1 and get out your f of negative x, then that tells you that you are an odd function. If they would have been the same, that tells us it's an even function. So let's find g of negative x. I have negative x to the fourth minus 2 times negative x squared. Negative x to the fourth is going to be x to the fourth minus 2x squared. I'm going to look and compare my g of x to my g of negative x. In this case, my g of x is the exact same as my g of negative x. So that tells me that this is an even function. When I plugged in the negative x, it didn't do anything to change what the original equation was. So I know that it's an even function. Last one, I'm going to do exact same process. Anywhere that there's an x, I plug in a negative x. I'm going to simplify. Negative x squared is x squared. 2 times negative x will be a minus 2x plus 1. So let's look at my g of x and compare that to my g of negative x to tell me if it's an even function. So I'm looking at my top and my bottom equations. Yeah, are they exactly the same? No, they are not, because this is negative in front of my 2 and that is positive. So they're not equal, so that tells me they're not even. Well, did I simply take a negative times, like my g of negative x is the same as my, oops. Oh, I keep saying g's. Sorry, we're dealing with h's. H, H, H. Is that the same thing as h of x? So did I take a negative 1 times everything in the original to get my second one? No, the only one that switched was my 2 in the middle. This isn't negative and that's not negative, so that doesn't work. Well, this one told me it was even. This one told me it was odd, but neither of those are true. So that means we have a neither. So it's kind of process of elimination at that point. So if you plug in negative x and you get the exact same equation out, you have an even function. If you plug in negative x and you get out a new equation, but it's the same as if you multiplied a negative 1 by the original, then it's an odd equation. If you do both of those things and neither of those are true, then it's a neither equation. Now I promised you a simple little trick, and I'm truthful on that. So I'm going to share another screen with you, if I can find it. Oh, it's still up. Cancel. It's still in here. I can just share it over here. So this is from your textbook. Remember, you have access to an e-textbook on the Canvas, or excuse me, on the Course Compass site. So here is a general thing. If every term, every variable has an odd power, remember your odd numbers are 1, 3, 5, so on and so forth. So if every variable in the equation has an odd exponent, then you have an odd function. If every variable has an even exponent, then you have an even function. If, like our last one, we had x squared plus 2x plus 1, so we had a variable that had an even and we had a variable that had an odd power, that's how we got the neither. So just from the very beginning, looking at our general equations, we can actually determine if it's even, odd, or neither without doing this plugging in math, the negative x thing, as long as you're looking at the powers. It says the constant term is understood as x to the 0, and so it works. This is where you have to check. It says h of x, x to the 5th plus 1 is a combination of odd and even powers, because they would understand that 1 being x to the 0 next to it, and 0 is considered even, and that's odd, so that would be a neither function. So that is where it gets a little tricky right there. That is why it is still good to plug in the negative x, but in general, you can look at the equations and just determine if it's even, odd, or neither. So hopefully that helps. The next type of function we're going to talk about is called a piecewise function. So a piecewise function kind of does two different things or more. It can do more than two things. And you're only looking at given intervals then that it does that. So our increasing, decreasing, and constant, the second example that we did, remember it was a straight line and then it jumped and then did a whoop. That's a piecewise. It did something where it was completely stable on an interval and then it jumped down and did an increase after that interval. And so that's what piecewise functions do. So here is a word problem that's a piecewise function. It says a telephone company offers the following plan. It's $20 per month, which buys you 60 minutes of talk time. Then you can have additional talk time for 40 cents per minute. We can write that as a mathematical equation, a piecewise equation, showing this, where the total monthly cost is in terms of C, and then the T is the amount of time we're spending. So it's two different equations, but it's for the same function. So it's $20 per month, whether you talk 0 minutes or all the way up to 60 minutes. It's after that that we have to add in the 40 cents per minute. And so it's 40 cents per minute after 60. So we have to subtract that 60 original that we would have already covered in the 20. So this is the two equations we'd be using. So we need to find out how much it's costing us with these two equations in our piecewise function. So part A, we're doing C of 30. So how much does it cost for our month if we are using 30 minutes of talk time? Well, according to our piecewise equation, if our T is between 0 and 60, then it's just 20. So there's actually no math to be done. We're just looking at the information they gave us, and it's 20. Now, if our T is greater than 60, we have to plug it in to this bottom equation, and that's what's going to happen in our second one. So we have 20 plus 0.40 times 100 minus 60. That's 20 plus 0.40 times 40, which is 20 plus 16, which is 36. So it's going to cost us $36 for that month if we use 100 minutes. So the way this kind of looks on a graph in a very general form, we have 20, 40, 60, 80, 120. Then we have 20 here. So all the way until we hit 60 minutes, which is right here, we have a constant function that stays at $20. After that is when it starts increasing. And so in general, it looks like that. So piecewise are pretty noticeable in that there's generally either a gap, like a jump in our graph, or there's this corner in our graph where it's like something dramatically changes. So this is how we compute values from a piecewise, but how do we graph a piecewise if we are given an equation? This one says f of x equals x plus 2 if x is less than or equal to 1, or we have f of x equals 4 if x is greater than 1. The way I always recommend doing that is doing each equation by itself. So pretend like we're just looking at f of x equals x plus 2. This is just a general, regular, run-of-the-mill line. And the way I've always told you to do this is we make our little table. with our x value, and we have our equation, and then we have our y value. And I've always told you to pick, 3 to 5 points. Make sure you have some negative, some like have a 0, and then some positive. And that in general is the case, but here you want to look for points that are going to fall in the range that they tell you. So I need my x's to be less than or equal to 1. So I'm going to do -1, 0, and 1. I still get a negative, I get my 0, and I'm able to do one positive number because it says that x has to be less than or equal to 1. Now I'm going to plug those in to my equation. So -1 plus 2 is going to give me a +1. 0 plus 2 is going to give me 2, and 1 plus 2 is going to give me 3. So then I can graph these points. 1, 2, 3, 4, 5. So my first point was -1, 1. So -1 up 1, there's my point. Then I was at 0, 2. Then I was at 1, 3. Notice I didn't extend my line past my 1, 3 spot, and that is because I know that my x has to be less than or equal to 1 on this graph for it to work. And so I don't want my x to go that way because that makes my x's positive, like more than 1. After that, I have f of x equals 4 if x is greater than 1. So it's going to be the straight line out of the 4, but we're going to use an open circle because we don't want x to equal 1 at that point. It says if x is greater than, but then we do have a constant function going off from that. And there is a piecewise function, a piecewise graph. So do both. Some people, I've had students in the past who will do 2 separate graphs. Well, they'll graph f of x equals x plus 2, and they'll graph the whole graph of that. And then on a separate graph right next to it, they would graph f of x equals 4. And then they would look at which piece they need from each of them and then do a third graph. And you can totally do that. If you have like erasable colored pens or pencils or anything like that, and you can do that where you do it all in one graph, that's fine. Or you can think through your intervals and know when you're going to stop. That's also correct. Any of those methods will work fine. Okay, the rest of my notes are just on the board. So I'm going to stop sharing so that I can make this big. Okay, last little thing from this section, and it's really just something we need to touch on. It's not something that you have to really memorize or be super like, oh, I can do the difference of quotients for a function. I just need to expose you to it and you can see how it works. It's a plug and chug problem. It's not difficult. It's just keeping track of like your variables is really what it is. So the difference quotient of a function simply states that if you have f of x plus h minus the original function, the f of x, all over h for h to not equal to 0. That's like, it's a definition thing, like you memorize it, and it's just telling you that it always works. This is always true. Okay, so if they give you a problem and they want you to use the difference quotient, what you have to do is you have to find f of x plus h, then subtract it and put it all over to h and simplify it down. And so that's what we're going to do. I'll leave that up there so you can see it for a minute while I do the first part. So generally, if you have an equation or if you have a problem where it's wanting you to use the difference quotient of a function, they're going to give it to you in multiple steps. They're going to ask you to find f of x plus h first, and then they're going to ask you for the actual difference quotient. That's just so that you can see the math, like it's not all one big conglomeration. You can do the math in pieces. So we're going to find the f of x plus h. What that means is anywhere in our original equation that we have an x, we are going to write f of x, or we're going to write x plus h instead, and then we want to simplify it out. So this is 2 times x plus h quantity squared, whoops, minus x plus h plus 3. So that's 2 times x plus h times x plus h. And then I'm going to distribute this negative in to both. So it's a minus x minus h plus 3. And I split up my quantity squared into 2 binomials so that I can do my FOIL method, where I have x squared plus hx plus hx plus, that's an x on the end, plus h squared minus x minus h plus 3. Now I'm going to combine. So I have 2 times x squared plus 2hx plus h squared minus x minus h plus 3. Distribute my 2 into everything inside the parentheses. So I have 2x squared plus 4hx plus 2h squared minus x minus h plus 3. And then I look, do I have anything that I can combine? I don't, because this is x squared and I don't have any other x squareds. This is hx and I don't have any other hx's. H squared, just regular x, just regular h, and a constant. So there's nothing else I can simplify, so that actually is simplified out. So then if I need to find my difference quotient, what I'm going to do is I'm going to take what we just found and I'm going to subtract that from the original, like the original subtracted from it, all over h. So that big long thing we just had, I'm going to write in there. I'm going to write 2x squared plus 4hx plus 2h squared minus x minus h plus 3, because all of that is my f of x plus h, minus, and then in parentheses, I'm going to write my original equation, which was 2x squared minus x plus 3. And all of that is over h, with the understanding that h is not going to be 0. So the only thing I can do is I can distribute my negative in. So 2x squared plus 4hx plus 2h squared minus x minus h plus 3 minus 2x squared plus x minus 3 all over h. Well, now I look to see if there's anything I can combine on top. I have a 2x squared and a minus 2x squared, so those are going to go away. I have a positive x and a negative x, so those are going to go away. And I have a positive 3 and a negative 3, so those are going to go away. This is always what happens with this. So I'm left with a 4hx plus 2h squared minus h all over h. Is there anything that these things all have in common? Yes, there's an h in every single one. So we can pull that h out front, so we're left with 4x plus 2h minus 1 all over h. And since it's out front and we have it on bottom, you can cancel it out. So that leaves us, I'm sure you can see it, with 4x plus 2h minus 1 as our difference quotient of a function. Like I said, difference quotient of a function, you just need to be exposed to it. You need to see how you really, it's just a plug and check. You plug in the information, you simplify it out. That's all we're doing. And that is the end of 2.2 over more functions.